Guys, Levy's going to drop a new album in 90 days. Oh my god. Oh my god. Bro, I can't wait, bro. I just like Levy music so much, bro. Just sign my autograph. Just sign my autograph. Wait, give me your autograph now. But okay, let's get over the fanboying. Man, I just like Levy music so much, bro. I also really hate periods. I hate periods. I hate periods so much. Oh my god. Okay. But bro, like 100% of my view base is men. Bro, that 1%. I hate periods. 1% of the females I hate periods. But let's do this with banked. So we're gonna do banked curves. Banked curves with friction. This is gonna be a little more complicated. But overall, the formula and the way you derive the equation is pretty similar to without friction. So in the previous video, I talked about what banked curves look like. But I'm just going to do a quick overview of it again. Banked curve, again, just an angled part of the road. It's kind of slant tilted so that normal force can contribute to your centripetal force to help you from swerving off the road in case your tires are very bad. Some people don't replace their tires when they're completely flat. So these civil engineers need to take this into account. But basically, we have a car driving along the slanted road, and we represented it with a free body diagram that looks something like this, with the normal force pointing in the direction perpendicular to the plane, and we also have our weight force. But this time, we're going to have the friction force, and friction is going to be parallel to the plane. So friction is either going to go in this direction or in this direction. So if friction goes in this direction, in the downward direction, acting down the plane, and that means you're going way too fast. If you go way too fast, your car is gonna keep going up and up the road until you fucking fly off. But due to friction from your tires, it's gonna prevent you from flying up and up the road until you fly off. But what if you're traveling too slow? Well, if you're traveling too slow, then friction is gonna act in the other direction. So friction is going to try to prevent you from falling down this bank. Well, friction of your tires between the asphalt is going to try to help you from falling down the bank. But for the formula we're going to derive, we're just going to use the example of you driving too fast around this curve, because usually that is the case for most drivers on the highway. I'm also going to show you the other derivation, but for this one, let's just worry about this for now. So we have a coordinate system here. The coordinate system is just the standard x, y. Okay, I made that too thick. I was making a thumbnail for the other video. This is the normal thickness that I use. So this is the xy axis. It's the xy axis, and this is y. This is x. And we're going to use our components of our normal force and our friction force and our weight force in order to derive a formula in order to solve for the maximum velocity, or the minimum. In this case, the minimum velocity, since your friction is maximum velocity, since your friction is acting in the opposite direction of your rotation. So if we take a look at this is our free body diagram. This is a normal force, a friction force, and a weight force. Well, the angle between the normal force and the y-axis is going to be theta, not delta, because if you had a rotated coordinate system, the angle between the weight force and the rotated coordinate system that is parallel to your normal force will have an angle of theta between the negative y. This is the negative y prime axis and the weight force. So it's going to be theta, and given vertical angles, you will form an angle of theta on the normal force. And for the angle between the friction and the negative x-axis is also theta, because again, in a rotated coordinate system, this is the x prime axis in our example. A rotated coordinate system, the angle between the x prime axis and the old x-axis, let's make this look better, is theta. Vertical angles, again, your friction force is going to be have an angle of theta between the negative x-axis, vertical angles. So I hope that explanation was somewhat reasonable for you guys. But now that we have the angles, we can also calculate and create equations for F nets equations. So for, net force equations. Let's calculate for y first. So there's 1, 2, 3. There's 1, 2, and 3 components in the y direction. So we have the normal y force, and we also have the friction y force. So friction y force, and we can add up. Oh, I wrote n of x. Okay, this is f of y. We have friction y force. So we can calculate all of these by doing a little bit of math. So the normal y force is calculated by, well, this right here is the y component as well. It's calculated by the normal force times the cosine of theta, and it is positive, since it's going in the positive y direction. The friction force is going in the negative y direction, so this will be negative. But friction is calculated by normal force times mu. So mu of s, usually it's going to be static friction in these cases, if you're not swerving off the road already. And the sine of theta, so because this y component of the friction is the opposite side of theta. So this is sine of theta minus mg, since weight also goes in the negative y direction. And this is all equal to 0. We also have the net x equation. So net x equation is, there's 1 and 2. Let's change the color of that. So 1 and 2. Okay, yellow on white is not good. I already did that in another video. What color should I pick? Orange? Orange, yeah. There's 1 and 2. So there's the x component of the normal force and the x component of the friction force. So the x component of the normal force is normal times the sine of theta. And the reason why I'm setting this as positive is because, well, it's just easier to do the math, and also they all go in one direction. So I'm just going to set them as positive, since there's no need to care about any other vectors going in the positive x direction, the true positive x direction. So we're going to set all of them as positive. And we also have our x component of our friction force, which is just normal force times friction coefficient times the cosine of theta. And this is, since all these forces are pointing towards the center of the curve in the negative x direction, this is also equal to the centripetal force. So these are the two things that actually contribute to our centripetal force when we're driving around a banked curve, or at least the two components. So what we do next is combine these two equations. So you always want to combine these two equations. But how so? Well, we don't know too much about our normal force. Whenever we're calculating things, it doesn't. When you're given a problem, you're not going to get. You're given usually theta, the friction coefficient, and the mass actually doesn't matter. You're given velocity or some radius, but you're not going to be given the normal force. So we can actually isolate. You can actually isolate the normal force and substitute them in for both of these equations. So n of mu of s sine of theta is equal to mg. Does that make sense here? I just move mg onto the 0 side, and then I can isolate n by factoring out n and then dividing both sides by the factored out equation. So sine of theta, and this is equal to our normal force. This is fixed to m here. It's equal to our normal force. So what we can actually do is, this time we can, let's separate this. We can isolate n here. So n sine of theta plus mu of s cosine of theta is equal to mv squared r. So we can substitute n into this equation here, and then we will get mg is equal to, not is equal to, mg times cosine, no, times sine of theta plus coefficient times the cosine of theta all over cosine theta minus mu sine theta. And this is equal to our centripetal force. So what we can do, as always, mass usually cancels out in a lot of physics formulas. So in the end, we get a formula of gravity. Let's actually just erase the masses. Mass can just cancel out here. We can erase the masses, and then we get a formula that looks like this. So given all our information, if we want to solve for, I don't know, maybe a minimum friction coefficient, we can isolate the friction coefficient. Or if we want to solve for a minimum velocity, we can isolate velocity. Or if we want to solve for some minimum or maximum radius, we can isolate radius. Now, this is an example of you driving too fast. So this is v max, right? And the reason why this formula is for maximum velocity is because of the fact that your friction is acting down the incline. So if you're driving too fast, you're going to go higher and higher and higher along this bank until you drive off the road and you crash into a tree, and then you hit a truck, and then that truck hits other cars. But how about for the case where the friction is going in the other direction? So for v min, what if the friction was acting in this direction? So you're driving too slow. So the friction of your wheels has to keep you up on the road, because you're going to drive too slow and too slow and too slow, and you're going to spiral off the left side of the road instead. So in this case where the friction is acting upward, up the incline, all you need to do is change your signs. So this is the y component of your friction, so we just need to set this to plus. This is also the x component of your friction, so we just need to set this to minus. So in the end, what you get is just a sign switch between these two trigonometric terms. So all you would get is a minus here and then a plus here if you were to switch those. So this plus thing is for v max if you want to isolate velocity, and then minus and plus is for v min. But if you understand the logic behind it, or the direction of the friction, then these two won't be too difficult to derive. So once we derive this formula, we can move on to some problems, and we can actually apply what we have derived here. So for this problem, it asks, a car rounds a banked curve of radius 65 meters at an angle of 15 degrees. If the coefficient of static friction between the road and the car is 0.7, what is the maximum speed at which the car can traverse the curve without slipping? So when it slips, that's when kinetic friction kicks in. So that's why we have the static friction coefficient in this case. And it's asking for the maximum speed before friction cannot keep the car within the curve anymore. So we just got to use this formula. We can actually isolate velocity here by multiplying radius on both sides. So we multiply radius on both sides to get, so this is mu of s cosine of theta. Cosine of theta minus mu of s sine of theta. And then we square root everything. Square root everything. Okay, that's a very ugly square root. Is equal to v max. Now, again, if this question asks for v min, you would just change the signs on these trig functions. So this would be minus and this would be plus, before the car would just fall right into the curve. That'd likely be, actually, most of the time that wouldn't even happen. Okay, but whatever. We're asking for the maximum velocity in this case. So all we have to do is just plug in all our values. So radius is 65 meters. The angle of banking is 15 degrees. And the static friction coefficient is 0.7. So once you plug everything in from here, velocity max equal to 27.55 meters per second. So your maximum velocity that you can travel before friction, the friction of your wheels, gives out, fly off the curve. So this problem is slightly different if a car takes a banked curve at less than ideal speed. So the friction is needed to keep it from sliding towards the inside of the curve. Therefore, friction is acting in the direction up the incline. So when friction acts up the incline, preventing the car from spiraling into the curve, then that means we just switch the signs of our trig functions here. So this becomes a minus and this becomes a plus. We're not calculating V maximum, we're calculating V min if we were to isolate velocity in this case. So what do we do? Well, we need to find the minimum coefficient of friction. So the hardest part about these problems are literally just going to be deriving formulas, the algebra. The amount of time it took to derive this took quite some time as well. But let's first get the correct units. So 1 kilometer is equal to 1,000 meters over 1 kilometer, and 1 hour is just equal to 1 hour over 3,600 seconds. The hours unit cancels out, and the kilometers unit cancels out, so we get left off with meters per second. So if you type that into your calculator, you should get, okay, you know what, I multiplied wrong, hold up. You should get 5.56 meters per second. Let's draw that M a little better. Meters per second. This very scared driver is driving at 5.56 meters per second. This kind of reminds me of those elderly people that drive at like 10 miles per hour on open street, bro. That shit is so annoying. Okay, but besides that, we have our radius, which is 100 meters, and we have our angle, which is 15 degrees. So let's write down all this information here and then save it, because we now have to do a lot of algebra. Because since we're solving for the minimum coefficient of friction, we need to we need to isolate mu of s here. So maybe you could try it, a little algebraic challenge, but okay, so I'm assuming you've tried it. So I'm going to do it now. G sine of theta. So this is a minus now since we're calculating for, this has minimum velocity. Mu of s cosine of theta over cosine of theta plus mu of s sine of theta. And this is all equal to v squared over r. But let's substitute v squared over r with a to make less things going on in here. So we have a here. Well, in order to isolate mu, every time you want to isolate a variable within a fraction, you want to get rid of the denominator. So let's get rid of the denominator here. Let's get rid of the denominator like so. Let's multiply both sides by the denominator. So you get gravity sine of theta minus gravity mu of s cosine of theta is equal to a cosine theta plus a mu of s sine theta. So now that we have this, we can move all the mu terms into one side of an equation to get gravity sine theta minus a cosine theta is equal to gravity mu s cosine theta plus a mu of s sine theta. So we can factor out mu here. We can factor out mu. Let's do everything vertically from now on, because I think we have enough space. So we can factor out mu onto the side of the equation. So we get mu of s gravity cosine theta plus a sine theta. And we can divide both sides by this term right here to isolate mu. So we get left with gravity sine of theta minus a cosine theta over all divided by this term right here. So this is gravity cosine theta plus a sine of theta. And all of that is equal to your static friction coefficient. And remember, A is equal to V squared over R, so we can actually just substitute that in like so. So once we substitute that in, we get gravity sine of theta minus V squared over R cosine of theta. Gravity cosine theta plus V squared over R sine of theta. And all of that's equal to mu of s. So once you plug in all these values that you got for velocity, so this right here is your velocity, plug in for your radius, and then plug in for theta, the theta values. And gravity is just 9.8. Your static friction coefficient should equal 0.234. So this is the minimum static friction of this icy road, minimum static friction coefficient of this icy road in order for the car not to fall into the center of the curve. So as always, if you have any questions, put it down in the comment section. Again, the hardest part about this is the algebra and deriving the equation. So I hope this video helped on that.